Question number 3, again, is going to be a repetitious version of the same things that we saw in numbers 1 and 2, just with fresh numbers. And that's something that we should be aware of for the remaining questions in this playlist. Virtually every question is just going to be a rehash of what we saw in numbers 1 and 2, just with different numbers and different words that are kind of shrouding these numbers at first in a layer of mystery that we just have to unpack. So in question number 3, we're going to go into this again a little bit more prepared, having seen a couple of examples already. We know we're looking for an initial value and a multiplier to raise to the power of x. So I'm going to read this question now with much more dedication to those two ideas, because now I can read with a more critical eye. I'm looking for information about an initial value first. And as I read, 1 million kind of jumps out to me. That seems to be what we're starting with, because on average 5.6% of these light bulbs burn out. 5.6 is a percentage. Percentages go with multiplier. So automatically I can feel pretty confident. I think I found the two numbers I needed. And notice I didn't have to spend nearly as long reading for information. The initial value is definitely 1 million. The multiplier, we have to do a little bit of quick mental math to turn the percentage into a multiplier, but that's okay. We take 100% of what we started with. Since 5.6% of light bulbs are burning out, that usually means we're losing light bulbs, so I'll subtract the 5.6%. That would give us 94.4% of light bulbs remaining. If I convert that to a decimal multiplier, 2 places to the left, that means my multiplier is now going to be 0.944 to the power of x. So I have my equation. That's looking good. Now I just need to read for the question part. It says, the city fails to replace the burned out bulbs. How long will it take for the city to have only one working light bulb? So I want to know when this whole scenario is equal to 1 bulb. So I'm going to set it equal to 1. And again, I'm going to use the exact same steps that I used before. First step, get rid of anything that's not directly connected to x. So this million that's multiplying the exponential part, let's get rid of the multiplication. I'll divide both sides by 1 million. So divide here and divide on the other side, which means I'm running out of space a little bit, but we'll deal. So that means I now have 0.944 to the power of x kind of on its own equals 1 divided by 1 million is fine to leave as a fraction, but you can convert it to a decimal if you want. That's 1 times 10 to the negative 6 if you look at a calculator, or 0.000001. Let me just double check. 2, 3, 4, 5, 6. Yep, okay, so we're good there. Now, same steps as always. We want to get rid of this exponential thing, which means we want to introduce a log into the problem. Log on the left-hand side and log on the right-hand side. If now you already know where this is going, and you're like, ugh, Herbert, do I really have to do that part? Can I just like fast forward? Of course you can. You can skip any steps that you want to if you feel like you know where this is going, so feel free to use any shortcuts that you want to take for familiarity's sake. I'll bring the x down to the front. X times log of 0.944 equals log of the same crazy decimal. Again, that's why it's helpful sometimes to take those shortcuts, because if you know where this is going, it saves you all this writing. X is multiplying, so I can get rid of the part that's multiplying by dividing it to the other side. Again, we're being much more expeditious at this point because we know where this is going. Those are going to cancel. X is by itself. Now it's a calculator problem. So, to save myself the time, I'll use some of my calculator features here. Log of that crazy decimal that I just got, so I'll copy paste, divided by log of 0.944 gives me 239.731. And I'll read that back to myself in the context of the question. If I go back and reread, it says, how long would it take for the city to have only one working light bulb? It's going to take 239.731, I'll look for this, months. Usually the unit of time is the unit in your answer. So the answers are often measuring time in these problems, and this problem was just the same. Now I can always go back and check just to be sure. There are lots of different ways I can do that, but I happen to have a graphing calculator. So if I had 1 million, let's see, there you go, times 0.944 to the power of x in my calculator, and if I quickly kind of teleport myself to around the 239th month, I can check the table. Yep, I went from 1.04 working light bulbs to 0.98 working light bulbs. Now obviously in this context decimals don't make much sense. You're not going to have 0.98 of a light bulb, but you can definitely tell why the model works. And you can definitely tell that between 239 and 240 is where we hit 1 exactly. So while the numbers as decimals might not seem like they make sense, at least you can tell why, from an algebra standpoint, the answer that we got makes sense in the context of the question. So now that you've seen this, put it into perspective. Do we understand how the log process works? Because if so, can you start to cut some corners? Can you start to bypass some steps? Can you start to do steps in your head or in your calculator? Feel free to start cutting those corners as you see fit, because the next example we'll do, question number 4, is again going to be very repetitious, and we'll set it up more and more efficiently every time we go.